Hi everyone, this is Miss Glazer, and I'm going to talk you through day 3 of infinite series. Mr. Murphy spoke to you about finite series last class. We're going to build off of that. We're going to be using similar formulas, but there's going to be kind of new conclusions that are happening. The main thing is, in an infinite series, it's not going to have a last term. So in our examples, we're going to see a dot, dot, dot. But to help us kind of figure out what are the sums of infinite series, we're going to use some finite examples to kind of see what's happening. So for example, in example 1, 2 plus 5 plus 8 plus 11 plus dot, dot, dot. Let's find the sum of the first 100 terms, and then let's find the sum of the first 1,000 terms and kind of see what we're noticing. So first we're going to use the formula to find what the 100th term is, which is what Miss Greenman went over in day 1 with sequences. So we're going to take the first term and then add it to the number of terms, 100 minus 1 times our common difference. So let's come and look up here. The reason I know I'm doing a common difference is because it said arithmetic. I'm adding 3 each time, so my D is going to equal 3. And so I'm going to put 3 right here. And so T of 100 equals 299. Now we're going to use the formula that Mr. Murphy went over in the last class, and we're going to do 100 terms divided by 2 times our first term plus our last term, or our term that we're dealing with, so the 100th term. And so that sum is going to equal 15,050. Now let's check out sum of 1,000. So again, first let's find the 1,000th term. So we're going to do 2 plus 1,000 minus 1 times, again, our common difference. The only thing that changed from our last one is instead of 100, we're plugging in 1,000. The 1,000th term ends up being 2,999. And so if we plug in to our formula for the sum of 1,000, we're going to do 1,000 terms divided by 2 times 2 plus 2,999. So again, it's the first term plus the last term of what we're trying to find the sum of. And so that's going to equal 1,500,500. So now let's just kind of make an observation. The partial sums are getting bigger, but how big do they get? In other words, as n gets larger, as the number of terms gets larger and larger, or goes towards infinity, is there a number that the series is approaching? Well, if you notice, for our T of 100, the sum of 100 was 15,050. And for T of 1,000, the sum of 1,000 was in the millions. So we can see as n gets larger and larger, goes to infinity, our value is actually heading towards infinity, the number that the series is approaching. And if the common difference was negative instead of positive, you hopefully guessed it, it's going to head towards negative infinity. So now let's look at example 2 with a geometric series. So in a geometric series, we got to first find the ratio that's happening in between. And so the r for this one is multiplying by a half each time. And so that's going to be our r. We're going to find the sum of the first 10 terms. So what's nice is, as you saw in the last lesson, we don't have to figure out the 10th term to find the sum of the terms. We just are going to use the first term of a half, multiply it by 1 minus our r, which happens to be a half also, and raise that r to the number of terms. So raise it to the 10 in this case. And then all divided by 1 minus our r. So just be clear that this 1/2 was our first term 1/2, and this 1/2 in both those positions is our r. Okay? It just happened to be the same number for this problem. But if we do that math out, we're going to get 0.9999999. The actual fraction is 1023 over 1024, but it's 0.999999999. Now the sum of 1,000. So same formula. We're taking the first term, we're multiplying it by 1 minus our r, but this time instead of raising it to the 10th power, we're going to raise it to the 1,000th power, and then all divided by 1 minus 1/2. So the only thing that changed in this problem was our n. The only thing that's changing in our formula for these problems. And so we end up with this equals 1. And so if we plot this series on the graph provided, so the sum of one term would be 1/2, 0.5. The sum of two terms, if we're just looking at the 1 plus a quarter, it's going to be 1/2 plus 1/4, which would be 3/4, or 0.75. The sum of three terms ends up being 7/8, or 0.875. The sum of four terms ends up being 15/16, which is 0.9375. And then we can see the sum of 10 terms we said was 0.9999. The sum of 1,000 terms is going to be 1. And so if we graph this, so our first term was about 0.5, or sorry, was 0.5. Our second term, 0.75. When it was the sum of three terms, 0.875. Sum of four terms, 0.9375. Oh, that one should be a little bit lower. Sorry. 0.9375. And then 10 terms was just below 1. And anything bigger is going to be hitting that 1. So you can kind of see, like, this almost relates to our asymptotes. Like, it's getting really, really, really close to that 1. And in this case, it hits the 1, but it's never going to cross the 1. It gets really close to 1, never going to cross it. And so as the partial sums are getting smaller and smaller, as n gets larger and larger, goes to infinity, the number of the series is approaching one value. And in this case, it's approaching 1. So let's take a look at another geometric example. Are we always going to have it that geometric is always approaching 1? So let's see. So in this case, our r is 2. The formula for this series, if we find, so again, the formula we're going to be using for this series, S sub n equals t sub 1 of 1 minus r to the nth, all over 1 minus r. And again, remember that r can't equal 1. Otherwise, it would make the denominator equal to 0. So now let's plug into our sum of the first 10 terms. So our first term is 3. We're going to do times 1 minus our r is 2, raised to the 10th, all over 1 minus 2. And if you put that into your calculator, keep in mind you want to do what's inside the parentheses first. And so technically you want to raise the power. So you're going to do 2 to the 10th power. You're going to do 1 minus 2 to the 10th power, then multiply by 3. If you're careful when you type it into your calculator, it should do it all correctly, but just make sure you're putting in parentheses correctly. And if you do it correctly, you'll get 3,069. The sum of the first 100 terms, again, same formula, 3 times 1 minus r is still 2, but now the n is 100, all over 1 minus r, or 1 minus 2. And if we do this one, we get 3.803 times 10 to the 30th. So, in other words, a really, really big number. 10 to the 30th, if we remember scientific notation, means to move this decimal to the right 30 times. So a really, really big number. And if we were to graph the geometric series, here's the graph right here. So you can see as n gets larger and larger and goes towards infinity, the number that we're approaching this time is infinity. And if you want to abbreviate it, we can use the symbol. So let's summarize what we've seen so far. The sum of an infinite arithmetic series always is going to approach infinity or negative infinity. And remember, infinity is going to be what we approach if the difference is a positive difference, and it's going to approach negative infinity if it's a negative difference. The sum of an infinite geometric series is sometimes going to approaches a number, sometimes infinity or negative infinity. Now, I'm sure you're wondering, well, how is there a way we can tell? So yes, how do we determine when a geometric series approaches a number? We're going to be able to tell whether it's a series that's going to converge or a series that diverges. If we have a series that converges, I'm going to change the orange, that's going to be when an infinite series approaches a number it is said to converge to that number. And I'm just going to jump down. If our ratio, the absolute value of our ratio, is less than 1, aka r is between -1 and +1, the series will converge. Now, if we have a series that's going to diverge, whoops, meant to highlight. If we have a series that's going to diverge, that's going to be when it does not approach a number, it diverges. And we'll be able to tell if a geometric series is going to diverge because the r will be greater than 1 or it will be less than -1. That's when it's going to diverge, okay? So again, to recap, the sum of an infinite arithmetic series always approaches infinity, negative, or negative infinity. It's going to approach infinity if d is a positive value. It's going to approach negative infinity if d is a negative value. And then for converging or diverging, that's when we're dealing with geometric. series. So we have a slightly new formula. If a geometric series converges, then we're going to be able to use this new formula. We just have to do the first term over 1 minus r. This is going to be the sum of an infinite series when it converges. So let's do some examples. So determine whether or not each series converges. If so, find the values to which it converges. So if we look at this first problem, we can see that we have to find our ratio. So we're going to do negative 10.5 divided by 42, which equals negative 1/4. And so if we look back up at our chart, or not our chart, above our new formula, because our r is between negative 1 and 1, our r is between negative 1 and 1, let me write it as a inequality. Our r is between negative 1 and 1, so this is going to be converges. And then it says find the value to which it converges. That's where we have to use our sum formula. So we're going to use the new formula. The sum equals our first term divided by 1 minus our r. So we're going to end up with 42 over 1 plus 1/4, or 33.6. In our next one, if we look at our r, 4 divided by 3.2 is going to equal 1.25. And since r is greater than 1, this is going to diverge. And we only need to find the value when it converges, because if it's going to diverge to infinity or negative infinity. And since r is greater than 1, it's going to diverge to infinity. So the last one, if we notice, this is not a this is not a ratio, this is a common difference. And so we get negative 1/3 as our common difference. And so as soon as it's a common difference, we know it's arithmetic. And so now we have to look and see, oh, it's a negative, so this is going to diverge. In number 4, it's telling it's a geometric series with t1, our first term is 60, and t sub 3 is 6 2/3. So we have our first term, we're missing our second term, but we have the third term. So I'm going to take our last term that we are given. I don't know why I keep wanting to write 3 on top. So 6 2/3 equals our first term times our r raised to the second power, because it's our number of terms minus 1, and since this is the third term. And so to solve for our r, we're going to divide by 60, and we're going to get 1/9 equals r squared. But don't forget, when we take the square root of r squared, we end up with 2 answers. And this even was trying to tell us, remember, there's going to be 2 answers. So r is going to equal plus or minus 1/3. And so when r equals 1/3, we got to do our sum formula. 60 is our first term over 1 minus our r, and we get 90. But when r is equal to negative 1/3, we now are doing 60 over 1 minus negative 1/3, and so we get 45. So that's it for the notes. I know there are some homework problems that you could be working on. Next class is going to be review day, and then the following class is going to be the assessment on sequences and series. So Hope you guys are all staying well. Miss you all. Have a great day.